Good. Good question.
And that means we should organize transportation.
So this will be part one of Adam's talk with us. So where were we last time? We were living inside the 3-sphere that sits as the equator of this 4. And inside that 3-sphere, we had a banded link, probably encoding a surface in normal form. And we had decomposed the banded link into 2 trivial tangles, with the band at first sort of surface framed by sigma, and then subsequently perturbed to lie in this little thing. Let me change this back so I can put my bar on the top. I don't know what the bar would have done to the bands. Okay, so our bands being surface framed by a bridge sphere, and with this bridge splitting up the link out. And so this was a banded bridge splitting. Banded B bridge splitting. And let's suppose that the size of the band set is n, and that we've perturbed B into B2 to be bands T2. And then we also had a membrane system for T2 that was dual to beta or B, or maybe the bands were dual to it. And then we also made the notational, we said we let B3 T3 be the result of taking T2 and resolving the bands. So this was sort of our setup. And what we had proved is, I guess, I'll call it lemma 1 since it's the first lemma that I'm recalling from last time, is that this B tangle, B3, T3, is trivial. So that's what we saw last time. But having put these bands in this particularly nice position with respect to this bridge splitting, this banded bridge splitting, we were able to achieve that when we resolved the bands for the tangle T2, the result was a new trivial tangle. So to start today, we'll prove lemma 2, which says the surface, this is going to be a special subsurface inside this 4. So we take T2 cross I, and then we throw in the bands at level set 0, and then we take T3 cross I. So this actually would be a subsurface of the surface in normal form here, because by definition that surface is vertical above each of these pieces. What about this trivial and this? Okay. So remember, the story is we have banded links that are encoding surfaces in normal form, and we went through this trouble of putting the banded link in this special position called a banded bridge plane. And so far that accomplished one thing, which was the result of resolving the bands as a trivial tangle. And now we're seeing the second thing it accomplishes, which is this surface, which is really the trace of resolving the bands, because we have the tangle coming up, then the bands are added, and then they're resolved, and then we have the new tangle going up. And the totality of this surface is triggered. So maybe I'll just a picture over here to guide our intuition. Okay, so what am I imagining? I guess down here at the bottom, I'm imagining, or let's, there should be a couple of pieces here. So I guess this bottom piece here is B2 -1 once, or -1 0. So I guess the bottom level is -1, the top level is 0. So up here we have B3, or the second half is B3, 0, 1. And maybe this front face is sigma. So sigma lives in the entire trace. That's the front face. And then we have a trivial tangle, which maybe I'll put in here as looking something like this. That, and this tangle comes up to this level. So this is the tangle. This is T2, -1 to 0. And then at this level, we get some bands, which probably just look like this. So there's B, and then maybe we'll switch colors to the top part and rising up. So this piece hasn't really changed. It's hard to get the perspective right when you start at the bottom. Yeah. So this piece is just a strand of the tangle cross I because it didn't have any bands attached to it. But at this one, we see a little saddle half. And so what do we want? Where do I want to sit here? Oh yeah, okay. Actually, look. So the result of resolving the tangle would be something like this. And so here we have like a sort of step, but actually, let's leave this part of mystery for now. Sorry, I got ahead of myself. Okay, but this is kind of the setup. So let's see what exactly is going on here. Okay, so we're gonna let B equal a collection, this dualizing collection of membranes through time -1 to 1, union the collection of bands from time 0. Okay, so this is actually what I want to draw. So what we see is we get these membranes. And these membranes delta 2 down here for our original tangle, and they rise all the way up through time. Okay, I did want to draw like this. So these membranes, cross I are just 3 balls. They're 2 discs cross I. And then we also add on this piece here, which is the collection of bands, or they're the bands cross I for 0, 1. So we sort of have a picture that looks like this. So this is the schematic for me. So the first thing we should observe is that diffeomorphic to to delta 2 union the bands from 0 to 1. So what do I mean by that? Well, B has these kind of pieces that are hanging out from the bottom, but this is just sort of a collar of the bottom boundary of B, so we could sort of just deformation retract this bottom half up into the top half. Okay, there's no extra topology being gained in the second half, so everything is happening right here. Okay. And then, so we want to recall that what was Y star? Y star was the intersection of B with the bridge sphere sigma. And we had that the shadows of these disks delta 2, union Y star is a collection of arcs. There are no closed components in that one manifold. And so the upshot of this observation is that delta 2 union the bands B is a collection of B minus N 2 disks. Okay. And so this is just look at the middle cross section. We've got these membranes, and then we've added some bands between them. A priori, when you have a surface and you start adding bands to it, you can get fairly complicated. Certainly, you can get complicated surfaces. But in this case, because we have this, because of the delta 2, we only get disks. So the only thing that ever happens is essentially what you're seeing, which is that one bridge disk is sort of attached to another. Another way to say this is that each, well, yeah, I mean, I guess there could have been, I drew the other day, there could have been a string of these guys attached with a string of bands. But in any event, the result will be this. All right, so all right, so then the upshot then is that this implies that this guy B that we originally started with is a collection of B minus N 3 balls. And then so the claim is that B is a membrane system for this surface, which maybe now I'll call D2. Which was T2 from -1 to 0, union band union T3 minus 0. Yeah, the claim is that it's a membrane system. So let's look at the boundary of B. Okay, the boundary of B has two sorts of pieces. The first is, let me just write this and let's try to figure out what I meant. Delta 2 B. One. Okay, so the first half of the boundary of B looks like this, or the first part of the boundary. And so what is this? This is the bridge disks at the bottom. Union the shadows of the bridge disks cross -1 to 1. Union the bridge disks and the bands at the top. Okay. Yes. And so in particular, this part is contained in, or this part is a collection of B minus N disks in the boundary of B2 negative 1, 1, which is, of course, a foil, right? So it's a collection of disks in this boundary and a span, a link J, which is given by T2 at negative 1 union the bridge points X from time negative 1 to 1 union T3. Okay, so J is the link that's this tangle union this vertical piece union the bottom tangle. And it's spanned by these disks that I've just described there. So that's part of the boundary of B. And then the second part of the boundary of B looks like T2 from negative 1 to 0 union the bands at height 0 union T3 from 0 to 1. So where is this? Well, this is sort of the inside portion of the boundary of B, right? You have this tangle going up, I guess, halfway. And so that's these sort of vertical pieces on the inside. Then you also have this tangle going up halfway. That's the other vertical pieces on the inside. And then you also have these bands, which are sort of, it's the bottom half of the yellow bit on the bottom. Okay. And this bit is, this is a collection of B minus n disks. Or well, so I guess the upshot is that this is necessarily B minus n disks. And the reason it's necessarily B minus n disks is because we have these B minus n disks on the boundary of these B minus n balls, one on each component, and so the other half of the boundary necessarily has to be with. Okay, does that make sense? So the claim here is that, well, I guess there's two claims. One is that this is a disk system, or a disk tangle, and the second is that it's a trivial disk tangle, because we sort of constructed the membrane system first. Any questions or comments? Everybody feel like they kind of get the idea? Okay, so okay, so what we're going to do is we're going to take all of that work we did and we're going to use it to show the existence of bridge trisections. So let's talk about that now. Let's see what we can do on next half hour. Okay. What is a bridge trisection? Bridge trisection has these two complexity parameters, one which I'll denote by B and the other I'll denote by the vector C, C vector, which will be 3 natural numbers. So bridge trisection of a surface length S in S4 is a decomposition. And we write S4S as the union of 3 pieces, Z1, D1, union Z2, D2, union Z3, D3, such that a couple of conditions hold. First is that we want, such that for each I in Z3, so considered cyclically, So I'll use Z-mod 3 to index these guys. So 3 plus 1 is 1. 3 plus 1 is 1. So the first condition is that each of these pieces that I've described is a trivial CI disentangle. And so here I'm invoking the fact that C vector is C1, C2, C3, which is an ordered triple of natural numbers. And then the second condition is that there are these manifolds BI, TI, which is the intersection of ZI, DI with ZI plus 1, DI plus 1. And this should be a trivial B-tangle for each I. And then the third condition, which I think is necessary to get all of these pieces to intersect in the right way, but I've always sort of avoided thinking about that too hard, is that there is a pair sigma x, which is the triple intersection of these pieces. And this is a 2B marked surface. Sorry, it's a 2B marked sphere. Okay. And then to just sort of keep this definition rolling, I'll introduce a bunch of terminology. Sigma is the core, or sometimes the bridge sphere. I think I'm on the side here. The BI are called flanges. The ZI are sectors. X is bridge points. The TI are called or the components of the data. Okay. If all of the C's are the same, then the bridge trisection is balanced. And we write that C bar is simply just the natural number C. Otherwise, it's unbalanced. Sorry, this is like a laundry list of terms just thrown right at you. And then just to establish some more notation, we'll let yi equal the boundary of zi, and we'll let li equal the boundary of di. This is for I equal 3. And then lastly, the union B1, T1, union B2, T2, union B3, T3 is the spine. That's important. I shouldn't have put it down in the corner like that. But anyway, so these are all the pieces of the bridge trisection. Okay, any questions about all of that real quick before any questions at all before so the next thing I want to do is just make a lot of sort of initial remarks about just remarks about bridge trisections. for how all these pieces interact. But before I do that, are there any questions? Okay. So the first thing to say is that we consider bridge up to ambient isotopy of this. So the two sort of bridge trisections in S4, if there's an ambient isotopy taking the spine of this bridge trisection onto another one, then we consider those two equivalent. So maybe I'll, oh yeah, go ahead.
So that's ambient 3-ball rail boundary.
No, I don't think so. Because in particular, no, in particular, the core can be moved. It's really just an ambient isotopy taking B1, T1 to B1 prime, T1 prime, B2, T2 to B2 prime, T2 prime. And then probably at that point necessarily B3, T3 to B3. So, I mean, the first thing you might just say is we consider two bridge trisections equivalent if there's an ambient isotopy taking sigma to sigma prime, taking the core of one together. But you have to worry a little bit there about, well, maybe you're permuting the pieces somehow.
Okay.
And so this sort of doesn't allow that. Right, so I guess if you do have two bridge trisections and you have an ambient isotopy taking the core of one to the core of the other, then you kind of have to ask, what is the permutation taking the 3 balls of one to the 3 balls of the other? It's either the identity or it's a cyclic permutation or it's a reflection.
So I know that's not a manifold, but could you consider it like ambient isotopy of that set well the obvious boundary of that set? So like the boundaries of the balls minus this?
No, I don't think so. I mean, I don't think you want to do anything real boundary.
Okay.
It's kind of like, think of it as like a banded link, right? We considered banded links were two complexes. And we could just consider the two complex up to ambient isotopy inside S3. This is a 3 complex.
Okay.
I think that's the way to think of it. Okay. Oh yeah, I was gonna draw like a little schematic. Yeah, this is probably good. So if this is S4, drawn in down 2 dimensions so that it looks like a sphere, then the 0-dimensional sphere here will represent our core sigma. And, or actually, this is sort of, it's worse than that. Oh, sorry guys. Sigma, I guess we'll leave this sort of arc like this. Yeah, I mean, this is not the world's greatest schematic, but it'll be at least helpful, I think. So we have sort of, this is meant to be B1, and then sort of inside B1 we have some tangle T1, and then we sort of have that somewhere else in the core sphere we have B2, and maybe inside here we have some other tangle T2, and then over here in third place we have some sort of tangle like this. Something like that. This is T3 inside T3. And then in between these things, we have these like Z1. This is useful for getting the indices right too. So let's see if I could consistent. I'm going to do it. So Z1 intersects Z2 should be B1. Oh, got it wrong. What are the chances? Let's change this to minus. Now it should work. So Z3 should be, or B3 should be the intersection of Z3 and Z2. And B3 is right here, it's the intersection. Okay. Oh, and then so what's the missing piece? Well, the missing piece then is also these disk tangles, right? And so what we require is that there's sort of this trivial disk tangle in here that caps off the union of these tangles. So now I'm getting a little bit ahead of myself. So let's mark down some of these remarks that I have. I have a laundry list of remarks as well. So the first remark is that Li inside Yi is a Ci component unlink in B bridge position with respect to sigma. Right? In other words, Yi Li is, let's see, let's get it right. This is where I get my things backwards. So this is plus. That's right. See, this is Y1. Wait, but that should be this. What's wrong? Oh, it's because it's the intersection. So it's going on 4 years. And I'm almost certain to get the Euler characteristic formula wrong. Okay. So this is +1 and this is -1. I see, because those are the indices on the B's and these are the indices on the C's. I'm happy. Okay. So that's the first remark, and so that's what we see here. So the boundary of a trivial disk system is an unlink, and it's naturally in bridge position with respect to this sphere, which we can, this is over sigma x. So we naturally regard sigma x as a bridge sphere in each of these three manifolds, right? So these three spheres, and they all sort of intersect, but okay, good. Oh yeah, great. Let's see if I can get into more trouble here. We orient, I don't know what the right way to say this. We let the orientation of S4 be such that, induces orientations on the Zi. I double so that in this sentence. First condition is that Yi is oriented as Bi union along sigma Bi +1 bar. And the second condition is that sigma is the boundary of Bi bar inside inside. Okay. Okay, I claim that this is an orientation convention that makes sense. I think I'm going to continue to draw red, blue, and green clockwise. I think that makes sense. I'm not happy about this thing that came up yesterday with like sigma being oriented down.
Just drew red, blue, green counterclockwise.
What did I do?
You drew counterclockwise, you said clockwise.
Oh, we want them to be counterclockwise, no? Oh, good. Well, that's how they are. Yeah, so Dave, I'll fill you in on this because you'll get a pick for this. Jason pointed out that when we draw these tangles in S3, we orient sigma like this, not as the, and we usually put tangle 1 here and tangle 2 here.
That's not, I mean,
But we don't normally, but then we always use to say that sigma is oriented as a boundary of B1. And so then this should be, how do you do it backwards? Okay. So sigma is oriented that way from now on. Thanks, Jason. Okay, remark 3 is that once we've put S into this bridge position, we don't have to define bridge position, undefined bridge position. Maybe I'll just say it out loud. So a surface in S4 is in bridge position if it's, maybe I didn't define that because I haven't defined the trisection. Anyway, if it's in position with respect to a union of 3 cross sections. But if we have a bridge trisection of S, then it induces a cellular decomposition of S itself. So the bridge trisection induces a cellular decomposition of S into C1 plus C2 plus C3 faces, 3B edges, and 2B vertices width. Okay. So the trivial disks are the 2 cells, the seams are the 1 cells, and the bridge points are the vertices. And so the upshot is that Euler characteristic of S can be calculated as this. So we can immediately read off the Euler characteristic of a surface given the bridge trisection parameters. The next remark is that S can be disconnected, and it can have non-orientable components. There was nothing at any part. Well, I guess we haven't really done it. There's nothing in the definition that describes this. Oh yeah, next remark. The core sigma should be recognizable as the unknotted 2 knot. I still can't bring myself to say 2 unknot, so I'm not going to. The core is it's this unknotted sphere that we talked about, right? And the flanges are fibers. Remember that we talked about how the unknotted 2 sphere is fibered in S4. Well, what we're seeing here is 3 fibers, and the bit in between the fibers is fibers cross I, and that's why it's 4. And so this is really pages in an open book decomposition of S4. Fibers. And then I guess the sectors are fibers cross I. Sloppy. Okay, and then the next remark is a good one. So let's start over. Okay. Is there anything that'd be particularly good to erase? Okay, the last remark, which I guess could be a proposition in its own right, I guess. So actually, let's maybe do that. Proposition, which is that the surface S can be uniquely recovered from its spine. Okay. And the reason for that is that the spine sort of it's sort of the natural boundary of these three four-dimensional pieces. And in each one, all we have to do is cap off and unlink with a trivial disk tangle. And we saw that any two trivial disk tangles in this four-ball are isotopic boundaries, so there's a unique way to do that. So we say that the bridge trisection, the entire bridge trisection and the surface that is being bridge trisected is encoded or determined by its spine. All right, so this is I just threw all the things, all the bridge trisection things. So does anybody have any questions?
So let me try again. So if you have two bridge trisections and you take the spine of the first one onto the spine of the second one by an isotopy of S4,
Yeah.
taking the three balls onto the three balls, that's the equivalence?
That's right.
Okay.
And by this remark, it will automatically take the four-dimensional pieces.
Cool.
Can you explain again how we recover this surface S by the spine of this?
Yeah, so when we have the spine, I can sort of redraw a little piece of it like this. That's our bridge sphere sigma. We have, say, one of our balls here, and say so this is B1, this is B2. And inside B1, we have some trivial tangle, and inside B2, we have some trivial tangle. But by the definition of a bridge trisection, this is an unlink. And so what we need to do is, to recover the trisection, is we just need to cap off with a trivial disk tangle. And the proposition that we proved, that was not membered or anything, but was that there's a unique way to cap off and unlink with a trivial disk tangle, because any two trivial disk tangles with the same boundary or ambient isotopic program. So there's even like sort of, one way to do this is to sort of take a collection of cipher disks, a spanning collection of disks for the unlinked in S3, and just sort of perturb them into the full wall. And then you do the same thing on each piece. And that necessarily is ambient isotopic to the original, whatever the original bridge section was. Does that make sense?
Yes. And so this might or might not be connected like the surface. It depends on it.
Oh yeah, the surface might not be connected, but these pieces will almost certainly be disconnected. I mean, it is possible you have only one patch in each of the sectors, but in general, you'll have many patches in each sector. And so you can just imagine when you put them together, either you'll be sort of globally connected or not. And based on what I just said, you should believe that it's easy to check that, right? You sort of you look at all your little bridge points, and you start, originally they're partitioned into 2B points, but you start inducing connectedness with this arc and this arc and this arc. Now there's B connected components. And then you use these arcs. Now there's only C1 connected components. And then you do the same thing in the other ones, and you get down to however many connected components. Because that's an observation, is that the maximum number of connected components is the minimum of the CIs. Okay. Good question. Anything else? Okay. So then, of course, the main theorem, the whole point of this is that every surface length S inside S4 admits a BC bridge trisection for some B in N and some C in N cubed. Maybe there was another remark I could have made. Since I promoted remark 6 to a proposition, I have a new remark 6, which is that B is greater than or equal to the maximum over I of the CI. by this remark, because we have a B bridge splitting of a CI component. Yeah, so by the way, maybe I'll just pause, like weeks ago, I was throwing all these weird questions at you guys about bridge splittings of unlinks and how many are there, determining when you can put two tangles together to get an unlink. So all of that should just become very clear why we care. Because exactly what we're doing is we're gluing trivial tangles together in ways to get unlinks. And by this theorem, that's encoding any knotted surface in S4. So we sort of a little bit backwards, but we started now we're okay. So what I was going to do next is prove this theorem, of course. But let's maybe, I only have 5 minutes, so it'd be silly to start. So let's postpone this. And maybe this will have the added benefit of me maybe saying a few extra things that will help make Adam's talk a little bit more. Something, a little more something. So what can I say? Okay, so for each I equals to 1, 2, or 3, we can let EI inside the 3-ball BI be a properly embedded disk. And we can assume that the boundary of EI equals the boundary of EI plus 1 for all I. And we can also assume that our bridge points lie in the boundary of EI. Okay, so I erased my schematic. You might ask what I'm doing here, but I'm really just, I'm taking a disk in each ball that I'm going to use as sort of like a projection plane for a diagram. So the union of these things, so this is another non-manifold piece. The union of these 3 disks along their boundary should look exactly like this. It's what we call a triplane. And we can use this to define a diagrammatic object. A B-C triplane diagram is a triple. It's a triple P equal P1, P2, P3, such that each of the PI is a planar diagram for a trivial B-bridge tangle. And the second condition is this pairwise condition, which is that if I take PI and I glue on the next one with the mirror, as we glue the mirror of it on, this is a planar diagram for a CI component unlink. Okay, so I've actually already given a couple examples of these. There was one here, but let's just do it a little bit more precisely. So the simplest one is you take sigma like this. These are your, so this is E1. What do I do? E2. Do I do E1 up here? E1. E2. E3. And in each piece we see a trivial tangle. So sort of schematically inside the 4 manifold, what we're seeing looks like this. But the sort of natural thing to do is to just split these up and treat them as 3 independent tangles, where we're just sort of remembering that they all have the same boundary. Okay. And when you do this, it's sort of straightforward to check then that they're all, well, this is really silly, but you can check that they're unlinks by just taking the mirror of a subsequent one and putting them together. So let's look at a slightly more interesting example and then we'll stop. So here's our triplane again. So this time we'll take a tangle that looks like this. That's a 2 tangle, and in this piece we'll put something a little more complicated. This, and then in the last piece we'll have this. And when we spread this guy out over here, what we see is we get this triple of planar trivial tangle diagrams. And we can sort of quickly check by putting the mirror of one tangle below the other that all 3 of these are pairwise unmixed. So this is an example of a 2-1 triplane diagram. And this is, of course, an example of a 1-1 triplane diagram. 1 bridge and 1 component for each patch. Okay, and the corollary to this theorem is that every surface in S4 can be encoded by a triplane diagram. So, great, thanks. See you Friday. See you at Adam's talk. Any questions?